you believe the freshmen and sophomores get to go on a field trip all morning today? They get to go on a field trip. They every freshman and sophomore, like the Greencastle, who wants to go play. Serious?
My brother said something about a play by a
Teen statistics like drugs and teen pregnancy and stuff like that.
How long?
I go till 4th hour. They come back 4th hour.
I'm gonna be the only one in my research class that's keeping stuff.
Because I don't have to deal with any of the freshmen in my church class.
They're supposed to not be back till 11, but it's not that long of a play, so I'm not really sure how they're going to keep them till 11. But my juniors, I have them in pride time. They're very upset that they didn't get to go on this field trip last year. And I said, apparently juniors and seniors didn't give it up on you on those statistics already. Like they're hoping to save the freshmen and sophomores from.
I saw it in the
But juniors and seniors are like, whatever.
It's too late.
There's no hope. That's how I see it, at least. But Barrett Freeman was like distraught on it. He said he was going to commit suicide. And in his note, he was going to leave, like, because he didn't get to go on the field trip. And I was like, do I need to report you for the guy about this? He's like, please do.
Who was Barrett or
Barrett. All right, so up until this point, every limit that we've taken, we've been approaching an exact value. Today, we're going to look at what happens if we take the limit as we get bigger and bigger, like what happens as x goes to infinity and negative infinity, and talk about the relationship there. So this is kind of just, again, I don't think we need to write it down, but remember that infinity does not represent a real number. It's kind of like just what happens as x gets really big, what happens as x gets really small. And we're mostly talking about the end behavior. And we've done this before, we just haven't done it with limits. If you think back to Algebra 2 and pre-calculus, remember when we would do like, as x approaches infinity, f of x approaches what? In like showing that it goes up or down, talking about even and odd functions. But now we can just talk about it more specifically with limits. And again, it just says when we say the limit as f approaches infinity, we mean as it moves further and further to the right. And so I feel like we have a good grasp of what infinity means, but I felt like that was some good words in your book that I know you're never going to read, so sometimes I like to just put them up here and make you read them, just in hopes that you see that your book kind of makes sense sometimes. Like reading math books is a skill that most of us don't ever want to partake in, but sometimes it says some stuff that's important. All right, so let's actually write some stuff down. Oh, the good old sandwich theorem. We can still use the sandwich theorem as we're talking about infinity. And so it says find the limit as x approaches infinity of cosine x over x graphically and use the table of values. We're going to do the table of values first. Look at my pre-cal chapter P test. I just want to throw this up here. Is this insane or am I just going crazy? Like I feel like that's the most A's I've ever had ever on anything. Like there were 11 A's here. Like there were just people that tied. 11 A's in one class. Not to make you feel bad or anything about me calculus last year. As long as I was on it. And in second hour, they were like, it was insane. Like I don't even know why I'm doing test corrections. Because it was. But then 6th hour wasn't as great. 11 A's, 1 B, 1 C, 2 B's, 1 F.
Wow, even like last year for our class, it was like 3 A's, and then just
But then 6th hour had 6 A's, 5 B's, 4 C's, 5 D's, no F's. But they didn't have C's, so.
But they didn't have any F's.
But they didn't have any F's, so you know. But they didn't have many A's either. But I graded second hour first, and every test I graded was just like A plus, A plus, and I was like, what is going on? I mean, I'm glad they're doing well, but it's just they all cheated. I know. Then that's what I think. Did they have? How did they all get?
We also have some notes. They care a lot more.
Yeah, they really do.
No, not joking. No.
It varies. It is interesting, like class to class, the differences. Like Jake Gould's class, they cared a lot. They were very competitive, and they all cared a lot. And there were just a lot of like engineer boys in that class. And then the next year, Sam's class, like I went from 16 kids to 8 kids. And some of them I was like, I cannot believe that they're taking calculus. I'm like, I'm not sure that this is a good choice for them. And I was like, oh man, it's going to be rough. But they did really well. Like they actually did better pass percentage than Jake's class did. So I always tried not to judge based on pre-calculus years, but sometimes I wonder. Sandwich theorem. We did some of this. I helped a few of you on the homework on this. We didn't actually do them in class, the homework questions, so we'll see how we do with this. But remember the sandwich theorem? Cosine of x over x without a graph is kind of a hard limit to take, whether it's going to infinity or going to a specific number. So the sandwich theorem says, what if we take cosine, which we know, cosine of x we know is bounded between -1 and 1. And what we can do with the sandwich theorem is we can take this and do some algebra to make it match this, right? And so I think we did one in class where we had to multiply by x. Well, this one's divided by x, and so we could just go through and we could divide everything by x. And what's supposed to happen with the sandwich theorem is I don't know what cosine of x over x looks like, but the outside functions, maybe I should know what they look like, and I would be able to take the limit of them. The difference part is now we're going to infinity. But that's the idea of the sandwich theorem. I can tell you when we have a test in here, there's definitely going to be one question that I ask you to use the sandwich theorem on and show me that you can do this algebra, and then you know I'm going to take the limit as x approaches infinity of the left-hand side, so of -1 over x. And I'm also going to take the limit as x approaches infinity of 1 over x. So now here's the big question. Do you remember what the graph of 1 over x looks like? One of those 12 basic functions that we did in pre-calculus. Wrote the domain and range of each one, and said you should know them. It's like a little library, your brain. And it's a rational function. There's asymptotes. Let's pick some points. Let's see what happens. What if I put like 1 in here? What would I get? 1, so I'm just going to do this. What if I put 2 in here? And what if I put 4 in here? What if I put 10 in here?
Oh, it's the one that goes in like this.
Right, like it's going to keep going down, and if you put fractions in here, like if you put 1/2 in here, it actually goes up like this, so it looks like this, right? That's what I thought. And then the other side, because this is negative, it would look like this, right? Vague memories of that now? I didn't see you when you did this. Is it the one that looks like, and then I thought you just stopped. I didn't know there was hand motions. We'll get there in a second. But 1 over x, then, if we're going towards infinity, that means I want to know what's happening as this is getting bigger and bigger and bigger and bigger. What is this getting closer and closer and closer to? 0, right? Because like if I put 100 in here, I'm going to get 1 over 100. If I put 1,000 in here, I'm going to get 1 over 1,000. If I put 1 million in here, I'm going to get 1 over 1 million. And eventually your calculator will just say that's 0, but it's actually just really, 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 really small. And so as x goes to infinity, the limit actually goes to 0. You did, and we're going to make that connection today. The horizontal asymptote of this would also be 0. Do you agree with me on that? And there's a big connection there between limits going to infinity is a horizontal asymptote. And that's where your pre-calculus book talked about limits, but I just avoided the talk of limits in pre-calculus. But yes, we already knew about limits, we just didn't call them limits. So -1 over x, do you remember what a negative does to your graph? It flips it over. And so since, I'll do green graph now and red lines here. Since this 1 over x is up here, -1 over x is just going to be the negative side. And since 1 over x is already negative, -1 over x is going to flip over. But as I put bigger and bigger numbers in for x, is my limit still going to be approaching 0? Because it's just going to be really, really small negative numbers. Think about it. If you put 10 in there, that's negative 1/10. If you put 100 in there, that's negative 100th, negative 1,000th, negative 1,000,000th. So again, I could say that it goes to 0 by looking at the graph or by making a table there, but I just kind of do the table in my head. So the fact is, I don't know what cosine x over x looks like, but I do know what negative 1 over x and positive 1 over x looks like. So this is actually, I think, a good one for the sandwich theorem, that I could give you something like this on a test, and I would expect that you know what 1 over x and negative 1 over x looks like, and you could do. Because now I can say, without ever looking at this graph, that the limit as x approaches infinity of cosine of x over x equals 0, because the limit as x approaches infinity of negative 1 over x equals the limit as x approaches infinity of 1 over x, which equals 0. That's kind of that whole justification, like saying the sandwich theorem says that's true. I could have been a little more wordy and said, by the sandwich theorem, but you don't really have to call it by name. We could look at the graph of those negative 1 over x and 1 over x, but we kind of already did that. So I said making a table of values first, but we really just looked at the graph. So we'll do a table in a minute. But the table would be, you just keep picking, let's do one of these here. If I was going to do the table for the limit of 1 over x, when you're going towards infinity, you're not going to just keep getting closer and closer to a specific number, because infinity keeps getting bigger, right? Like, think about when we were getting close to 2, we would pick like 2.1, 2.01, 2.001. If you're going towards infinity, you need to pick big numbers. So like I always say, like, pick like 10 and 100 and 1,000, because you're just getting infinitely bigger. You don't have to pick those exact numbers, but you want to keep getting bigger, and usually powers of 10 work really well to pick to see what's happening. And so like if I picked 10 here, I get 1/10, 100th, 1,000th, and you can see if it's getting closer to a specific number. Or sometimes it just goes to infinity as well, and there is no limit that we'll talk about. So that's what it means by a table as opposed to a graph. So there is a direct correlation here between asymptotes and limits. So let's see, I think that's my next slide here. I might be going off, but okay, here we go. This is the way I told you to do asymptotes in pre-calculus and algebra 2. It's still a way that works for rational functions. If you forget this way, you might want to write it down again. It's how you look at the numerator and the denominator. It definitely shows up on the AP test, and if you know this shortcut, it's usually a quick way to get the limit. The restrictions for this is it only works for rational functions. And so we'll talk about tomorrow what are ways we can find asymptotes or limits if it's not rational. And so I just wrote this as n of x over d of x, meaning the numerator over the denominator. And remember, it's all about the degree of the numerator and the degree of the denominator. And so, I think I crowed this. And so the great thing is, if you know this rule, is really easy, but you have to remember it. So that's where maybe learning a different way is going to work. But if the degree of the numerator is smaller than the degree of the denominator, like the one that we just did, 1 over x, then it's always the x-axis. The line y equals 0 is a horizontal asymptote. Remember, if the numerator and denominator have the same degree, that's where you have to take the leading coefficients. So that's what I wrote there, a sub n over b sub n. It's the leading coefficients, and we'll look at one of those in a minute. bigger than the denominator, you are going to have no horizontal asymptote, which also means no limit as x goes to infinity, because we're going to write just a minute, horizontal asymptotes and limits going to infinity are the same thing. That's because if the numerator is bigger than the denominator, your graph's going to just keep going towards infinity or negative infinity as well. So again, this is not new. The new part is that whatever your horizontal asymptote is the exact same thing you would get as you take a limit going to infinity or negative infinity. So the new way, or the calculus way, is that if, well, I'll just write it. That actually says x approaches infinity, x approaches, and that's a negative infinity, but it kind of like pushed it all together. So this says if y equals b is a horizontal asymptote, then when you take the limit going to infinity or negative infinity, you're going to get that number value, that b value. I like to think of it the other way. If you take a limit going to infinity or negative infinity and you get a number, like we just got 0 on that 1 over x, if you get a number, that's the same as a horizontal asymptote. So I cannot stress enough this correlation. Horizontal asymptotes equal the limits as x goes to infinity or negative infinity. And so this works for everything. The hard part is sometimes a chart or a graph is kind of needed, especially today, and then tomorrow we'll kind of get into some algebra ways that we can use to do this. But horizontal asymptotes, limits going to infinity, are the same thing. So let's look at one here. And you're going to see today on your homework, they're kind of stressing this relationship, so you're going to get the same, like you're going to have parts A, B, and C, and you're going to see that you're repeating your answers, because they're going to ask you what are the horizontal asymptotes, they're going to ask you to find the limits going to infinity, and you're going to see that they equal the same thing, hopefully to kind of stress this relationship. Alright, so, here's another problem for you. It says, use a graph and tables to find the limit as x goes to infinity, the limit as x goes to negative infinity, and identify all horizontal asymptotes. And they even gave you the graph here in this one. You don't have to make that graph perfectly, you just need to kind of sketch it, sort of. And the big thing, the reason I stress this so much, is a lot of times on the AP test, on the no calculator part, it'll ask you, find the limit as x goes to infinity of a question like this, but you have no calculator. They want you to remember that it's just a horizontal asymptote. And you can use the little shortcut rule about the degree of the numerator and the degree of the denominator. And so we'll definitely hit this again next semester when we start our review, because limits are a long time away from that. Like, we forget things, but really kind of important. I'm going to do a table on part A and part B just to show you how you can use a table if you're not allowed to use a graph, or just to help you verify your results. definitely can look at the graph on this, but I just want to show you again, if I'm going to infinity using this function, I could pick like 10, 100, and 1,000. And if there's a horizontal asymptote, if there's a limit as x goes to infinity, I should see that these are getting closer and closer to the same number. If I plug 10 in there, still isn't so bad without a calculator, but if I plug 10 in there, I'm going to get 11 over 10. You agree with that? Which is just 1.1. If I put 100 in there, what are we going to get? 101 over 100, which is, move over 2 places, that's 1.01. If we put in 1,000, we're going to get 1,001 over 1,000, which is 1.001. So we can definitely see from the graph that as x is getting bigger, my y values are just getting closer and closer to 1. So I could say for part A, using my table, I'm pretty confident that my limit is 1. For part B, if I'm going towards negative infinity, what kind of numbers would I be picking? What could be my numbers in my chart? Negative 10, negative 100, negative 1,000. And again, I know this one's kind of maybe silly to make a chart, but I just want you to have one in your notes. And you can probably see from the graph that it should be the same as x approaches infinity on this one. They're not always the same. Sometimes you have 2 different asymptotes, especially if it's not rational. But if we plug negative 10 in there, we're going to get negative 9 over 10, or negative 0.9. And then we're going to get negative 99 over 100, or negative 0.99. And then we get negative 0.999. Oh wait, that shouldn't be negative, right? That should be positive. Because it's a negative over a negative. Go with me on that. And that's where a graph is nice to verify that. Looking at my graph, that's definitely not an asymptote of negative 1. It should also have an asymptote of 1. Or a limit, sorry. So, you don't have to do that on your paper Thursday if you recognize that what you did in A and B is the same thing as you're doing in part C. And in part C, you can use the old way here. The degree of the numerator is the same as the degree of the denominator, so your asymptotes or your horizontal limits, horizontal asymptotes or your limits going to infinity is just 1 over 1 or 1. Follow me on that? I'm repeating myself a lot, but kind of super important. So horizontal asymptotes are what you get as you take a limit going towards infinity or negative infinity. We can also tell where our graph has vertical asymptotes using simple limits. So let's look at that real quickly. We're going to talk about my favorite graph here, 1 over x again. So we've already had this a couple times in lesson 2.1 of getting an answer where your graph keeps going on forever. So we got an answer of infinity. And the definition there of an infinite limit is a limit in which f of x increases or decreases without bounds as x approaches some specific value, some c value. And so I'm going to make a little graph again. We're not going to have to make it too perfect here, but one would be at 1, and then like 1/2, and then 1/2 here would be at 2. So it looks something like this. And this side would look something like this. So let's look at what's happening as we approach 0 here. And we're going to actually look at both the left and the right hand side. Alright, so I said, what's the limit as x approaches 0 of this function? To do that, let's look at the limit coming from the left and the limit coming from the right. So if I look coming from the left of 0, and I could make a table here as well, but I'm just going to look at my graph here. If I'm coming from the left of 0, what's happening to my graph as I get closer and closer and closer to 0? It just keeps going down, right? The y values just keep going down towards infinity. Negative infinity. So could we say that that actually equals negative infinity? And what happens as I'm coming from the right side of 0? What's happening to my graph as I get closer and closer and closer to 0? It just keeps going up. So it's going to go towards positive infinity. So what about the limit itself at 0? What would we say? Well, one side's going to positive infinity and one side's going to negative infinity. So they're definitely not approaching the same thing. And really, when you get infinity or negative infinity, remember I said that's not really a number. So the best answer here would be that there is no limit because it doesn't approach a specific value. And let's see, I wrote this here. Maybe if I can. Right? The limit does not really equal infinity or negative infinity. It shows that there is no limit. The big connection I want you to make here is, what's the vertical asymptote of this function? 0. So horizontal asymptotes, when you take the limit going to infinity or negative infinity and you get a number, that number is your horizontal asymptote. Vertical asymptotes, we're going to write this on the next slide here. If you take the limit of a number and you get that it's infinity or negative infinity, then you know that there's a vertical asymptote. All right, so they both have to do with infinity, but they are definitely different. So I want you to write this out on the next page here. This is kind of our other super important thing of the day. How do we relate vertical asymptotes to limits? The big thing is, if you get that the limit is going to infinity or negative infinity, then that means it's not continuous there, right? There's a break, there's an asymptote there. I got one more example I want to look at. And again, on your homework today, you're going to see we're trying to push this idea that when you have a vertical asymptote, your limit should be infinity or negative infinity on either side of it. No crutches. Officially off the crutches. Hope I need donkeys this weekend. We've been finding vertical asymptotes since at least algebra 2, because we know a vertical asymptote is where the graph is undefined for x. So when they ask you to find a vertical asymptote, you don't have to do anything new. But what you're going to see on your homework today, and I actually have number 3 today, we're going to skip this. This is really number 3 now. It says find the vertical asymptotes of the graph and describe the behavior to the right and the left of each vertical asymptote. And they give you the function. tell just from the function where the graph would be undefined, right? Yeah, you set the bottom equal to 0, and what you get when you solve it, usually your vertical asymptote. Sometimes it's a hole in the graph and it cancels out with something on the top, but in this one it's definitely not going to cancel. So if you wanted to just find your vertical asymptotes, you don't have to do any calculus to do this. Your vertical asymptotes, I'm just going to set the bottom equal to 0. And maybe you just know by looking at it. You don't have to do the algebra if you know. I'm going to subtract 4 and divide by a negative, and I get plus or minus 2. To see what's happening on either side of it, I'm totally fine with you using your graphic calculator to get the graph of it. But if those are vertical asymptotes, what's happening to the left and the right of each one should be infinity or negative infinity. And if that's not true, then that's not really a vertical asymptote. And that's the big connection there that we're trying to make. I'm going to tell you what this graph looks like just to save time here. So we have an asymptote here, and negative 2, and 2. And in the middle, this one is a lovely little parabola. And then this side looks something like this. And this side looks something like this, which you could use your graphing calculators to graph. What your homework wants you to do today is find the asymptotes and then tell me what's happening to the right and the left of each vertical asymptote. So I'm going to write it like a limit. I'm going to say what's happening as x is approaching 2 from the right, and what's happening as x is approaching 2 from the left. We have to do the same thing for negative 2. What's happening is x is approaching negative 2 from the right and negative 2 from the left. And the good news is if you know that asymptotes go to infinity or negative infinity, you have a 50-50 guess there, but hopefully you don't have to guess if you have a graph. If I'm looking at 2, here's 2, to the right of 2, that would be this side, right? Like coming in like this. That graph is going down, so I would say it is going to negative infinity. Everybody follow me on that? So you have to look at the graph, because sometimes they go up, sometimes they go down. If I'm looking at x equals 2, but I'm coming in from the left side, I would be up here on the parabola part, and it would be going towards infinity. You kind of follow me on that? This one would be negative is going negative, and positive is going positive. Your homework is on your assignment sheet, but here it is if you don't have an assignment sheet. Big connection. Horizontal asymptotes, vertical asymptotes. We'll do some more tomorrow. This is calculus time. We just heard the bell. Or that too. See you later if you have questions.